Okay, hi everyone. Welcome to a new Flan Talk. This week we're going to have Parsa Mirtaheri talking about the paper Let Me Think, a long chain of thought can be worth exponentially many short ones. Please go ahead.
Hi everyone, thank you for having me. I'm excited to present our work. Let me think a long chain of thought can be worth exponentially many short ones, which is a joint work with Ezra Edelman, Sami Jelassi, Eran Malach, and Enric Bosch, etc., and will appear in New Reefs next week. So, inference time scaling has emerged as a new paradigm for improving reasoning in language models where you just spend more test time compute to enable deeper exploration or enable more exploration and improve reasoning. And it is also a key component of frontier reasoning models such as OpenAI O series and like the Gemini thinking mode or the well-known DeepSeek R1 model, which was the first one to show openly that doing RL on the chain of thoughts of the models can enable longer chain of thoughts and eventually better accuracy for mathematical tasks. And they observed that the length of chain of thoughts increases with RL as well as the accuracy, which is something we will get back to it later. But while many different approaches have been proposed for scaling test time compute, they mainly fall into two categories. The first one is parallel scaling, where you generate multiple independent chains of thought and aggregate them with like a reward function or just an aggregator method and um, output a single output based on your generations. The other approach is sequential scaling, where you generate longer chains of thought so that you enable deeper exploration and you hope that the accuracy of your reasoning improves with that, which was something that as I mentioned, was done with RL, but it was also done with different approaches like appending weight tokens to the chain of thought and forcing it to generate longer thoughts. So in our paper, we take a step forward in understanding the trade-off between these approaches, especially because parallel scaling has its own computational advantages. You just need to generate chains of thought in parallel and also avoid longer contexts. One question is that whether it's enough, like it can replace sequential scaling, or sequential scaling is um, inevitable in some cases. And in our study, we focus on a graph connectivity task, which is just a variant of a more classical graph connectivity task, which we call ST connectivity. ST connectivity is that you're given uh, a, an undirected or on in other variants directed graph G nodes S and T, and you ask whether S and T are connected or not. And it is one of those problems in complexity classes which people study, like the expressivity of transformers by studying whether they can solve this task or not. Um, the problem with this task for us was that here the connectivity can be proved by providing a path from S to T, but this connectivity needs a more complicated evidence. So we designed an equivalence task, which is ST1, T2 connectivity, where you just basically copy that graph and you besides S and T, T1 or T2, one of those. In one connected component, you have another replicate of T in the other component. And given these um, graphs, like by some randomly labeled vertices and randomly ordered edges, The task is to decide whether S is connected to T1 or T2. And we are promised that exactly one of them holds. So here the proof can always be provided by just a path from S to T1 or T2. And later we use that to verify the chain of thoughts. So here is our task, our fundamental task, which we consider as a very simple test bed for multi-step reasoning. And specifically, we design these bridge graphs, which are parameterized by four parameters. And it's just composed of these components connected together. These components have like a short path connected to a longer path and a dead end path attached to it. So these are three parameters, and when you attach many of these together, you just get a bridge graph. And the point is that, and we also choose S as the leftmost one node here, and T, one of those T's as the rightmost one node. And the point is that to find a path from S to T, you can either go through these optimal paths, which are the shortest path, the longer one, or and you have to avoid these dead ends. So we consider the graph connectivity task on these specific tasks, which are parameterized by these parameters, and specifically we study for different depths. Uh, and having defined the task, we fix one bridge graph and generate many randomly labeled instances of it. Here, for example, you see one instance for a fixed bridge graph of with these parameters where the nodes are randomly sampled, and there is also a replicate of that graph because we have two graphs. And we encode this graph as a randomly ordered list of edges to get this input prompt, where you're given the graph and the task. And having defined the task, now we want to train models to solve this task. And we are interested in training models with different sequential scales. And by sequential scale, I mean just different token budgets for the chain of thought. And to do that, we train models with different chain of thought strategies. For example, we train a model just on the shortest path as the chain of thought. So there is the task, and the model is supposed to generate the shortest path from S. It is given in training the shortest path from S to the node in the target node that is reachable, and at the end comes the decision, which is either T1 and T2. This is the most efficient chain of thought we consider, which is just composed of the optimal path. Another variant we consider is the model trained on paths from S to the reachable target. And how we generate these paths for training data is that we run a depth first search starting from S. And the depth first search just explores the graph in uh, and choosing one of the unvisited nodes randomly at each node until it reaches the target. And here, for example, you see that the model goes down and then backtracks from it and then continues until it finds the target node. So we run DFS to find a path, but in the chain of thought, we just include the found path. We don't include like these backtracking steps. And this one is might like include suboptimal paths, so its chain of thoughts would be longer than the other model, but still it's just composed of paths. The longest chain of thought model we consider is trained on DFS traces. So similar to the previous case, we run a DFS from S, but this time we also include those uh, all nodes that are visited in the depth first search. So here, for example, it goes to the dead end, so we also include those nodes that come in the chain of thought and then continue uh, having the other nodes. So it's basically the list of visited nodes in the DFS ordered by uh, the visiting order. So this one is the longest chain of thought we train on for having the DFS model. And so these models are trained to generate chains of thought. To verify their outputs, we just uh, apply this verification function, which just checks that the model, the chain of thought, which is composed of a list of edges, it starts at S, ends at either T1 and T2, and every node in the list should have a neighbor earlier in the list. So that just basically is one um, relaxed way of proving that S and T1 or T2 are connected, because each node here has an edge connected to one of the previously visited nodes, listed nodes in the list, and it starts with S and ends with T1 or T2. So if a chain of thought passes this method, it can act as an evidence for solving the task. So having done training with these models, then we, so just to remember, we have fixed the bridge graph, but and then train the models for a fixed graph. The only randomness comes from the order of the labeling of the nodes and the order of edges in the input. So we do training and test the models for various depths. For we have fixed the other parameters, so the depth is the only one that's changing. And what we observe is that the short chain of thought models, the shortest path and path models, they get exponentially small accuracy in the depth of the model, while the DFS model, just a single generation from the model solves the task. And to find what this comes from, we look at the next. Uh, we find that this probability of success matches closely with probability of in distribution DFS traces for each case. Let me explain what that means. For example, for the shortest path model, the probability that a DFS trace stays in distribution is the probability that you run a DFS from S and your DFS, which randomly chooses one of the unvisited nodes at each time, um, doesn't go to any of these dead ends and these suboptimal paths, and it just traverses the shortest path, which has an exponentially small probability in D, which is the depth of the graph. That's what I mean by the probability of in distribution DFS traces. The probability of those traces in that are shortest paths, which here is it's just this single one. For the path one, there is more flexibility. It can choose these longer paths, but it still has to avoid these dead ends. So it still has as an exponentially small probability. But you notice that while this value perfectly matches the performance of the shortest path model, for the path model, it is a bit different. So the path model slightly performs better than just this. And by looking at the performance of models at different sequential scales, for example, here the blue line is showing the accuracy of the DFS model at each maximum length For example, here, if you limit the model to generate lengths of at most 32, you get half accuracy. So the interesting thing about this plot is that first of all, the DFS model, although it is uh, more, it's not as efficient, it's not supposed to be as efficient as the path and shortest path model. It outperforms the other models at every sequential scale. And as you see, yeah, these models, although they are trained to like output the shortest path, they fail to do so. So at every sequential scale, the DFS model is the best. And in the future, in the next slides, we will use the DFS model to control the sequential scale. The other interesting observation is about the path model. Here, the dotted red line shows the maximum length of uh, path traces the path model was trained on. So it was never trained on chain of thoughts longer than 26 for this example, for example. But you see that with increasing the length of chain of thought further than that, still the accuracy increases, which shows that there are some um, out of distribution success traces where the model generates a chain of thought longer than any seen during training, and they get verified and the model's accuracy increases, which is something that we will get back to later. But now that we have discussed sequential scaling, it's time to discuss parallel scaling so that we can study the trade-off later. For parallel scaling, as I mentioned earlier, parallel scaling means that you want to generate many chain of thoughts from your model and aggregate them to a single output. So you have to decide which aggregation method to use. We consider two different aggregation methods. One is majority voting, which is very common like in practice, where the chain of thought itself is not verifiable. So you only look at the final answer in many chain of thoughts and you take majority over them. And the other aggregation method we consider here in our case is the what we call best of n, but it's basically verifying all the chain of thoughts and see if just one of them passes the verification. Because if either of them passes, then that is evidence for the solution, so that would be enough. So we do this, and first of all, we saw that uh, the models had exponentially a small chance of success, so you can also predict the scaling of this verification uh, aggregation method, which closely matches with what happens in practice. So you need exponentially many generations. Um, but the other observation is that although um, this is based on verifying the chain of thoughts, it scales better than the majority voting over the decisions. And the reason is like the majority is always noisy, but here you only need one of the chain of thoughts to succeed. So we observe that the parallel scaling with this best of n scales better. So for parallel scaling, we will adopt this one. And now that we know how to control the sequential scale and parallel scale, we can study the different combinations of them and how they perform for our specific task. So here is the result for the transformers we have trained from scratch on this graph connectivity task for a fixed uh, depth and other parameters. And where the sequential scale is the token budget for each chain of thought, and the parallel scale is the number of independent chains of thought. And we do the same experiment with just the pre-trained large language models and observe a similar trend to our experiments. And the trend is that sequential scaling has an exponential advantage in the short chain of thought regime. So if you don't have long enough chain of thought, then just to if you decrease the sequential scale, then to match the same performance, you need exponentially many chains of thought. So here is where like a single long chain of thought can be worth the exponentially many short chains of thought. And we also replicated it for other language models, but I just put one of them. So now I want to switch gears to some theoretical evidence we have in addition to our experiments. But if you have questions about the experiments, I'm happy to answer what I can get. Okay, great. Let me continue with the theoretical part. So for the theory, we provide two different evidences. One is based on a computation model we introduced called vertex query model. The other one is based on previous results on transformer expressivity limitations and what we build on top of them. So we observed that the model's accuracy, the ones we trained, their accuracy is captured by the probability of in-distribution DFS traces. So for example, a model uh, trained on the path examples, its accuracy is equal to the probability of those paths in the distribution of DFS traces. And what this basically means is that no matter how the model was trained, like it was trained on shortest path, or the DFS, at inference, what happens is that the model cannot distinguish these unvisited nodes from each other. So at inference, even though you have trained your model to generate the shortest path, the model just randomly picks one of these neighbors because it cannot look ahead to see which of them lies in the shortest path. So it actually acts like a DFS model. It has to randomly pick one of them, although the graph is always there in the context. So it has the information there. It has the enough data that was trained on, but because of its limited expressivity, it cannot look ahead to distinguish these neighbors. And inspired by this observation, we define a vertex query model for the computation inside the transformer. And we say that an algorithm for this task is implementable in this vertex query model if initially it is given S, T1, and T2, and it can only access the graph through neighborhood queries, which is that it can query a vertex to an oracle, and the oracle returns the set of neighbors of that vertex. For example, like here, it can only see the neighbors of S, which is the first node, and then it can continue by querying the other ones. In the vertex query model, it can query any node, but we also define another variant, which is restricted vertex query model, where the algorithm is constrained to query only the returned nodes so far. So it can only start with S, and then it returns the neighbors that it can query the neighbors and continue so on. And so we define this inspired by our observations and also like previous results on the uh, limited k-hop reasoning of transformers with a constant depth. So you can also think of it as here you have just one hop that's just the neighbors, but because with limited depth you have limited k-hop reasoning, you can also model it as a larger neighborhood, but still it is a local neighborhood. So for this vertex query model, we start by considering the graph connectivity task on two disjoint paths. And what we can prove for this task as a warm-up is that while L queries are always enough to this task because you can just start from S and query them one by one until you reach either T1 and T2. With L over 2 queries, you have no chance of success. So theta L queries are always needed to solve this task. And queries here correspond to the length of chain of thought in our case. So here you need at least you need exactly theta L chain of thought to solve this task. If we think of each token generation as a query to the vertex query model. Then we switch to prove a similar result for our bridge graph connectivity tasks. And here we consider the restricted vertex query model. And the result is that sequential scaling succeeds. So if you query this much, if for a fixed for a fixed value between 1 and 0, with this many queries, there must be an S space here. So here we are considering a bridge graph with L and 2L as short and long. There is no dead end here. So you need this much queries, D and D is the depth. 2LD queries to solve the task, while with less than this much queries, and there are some typos here. With less than this much queries, you have exponentially small chance of success. And the idea is that you can define a algorithm, any algorithm, and find the expected number of queries needed to solve the task, and by just concentrating inequalities, you can show that this much queries are always required. And note that this is longer than the chain of thought. So this rules out like the possibility of learning the task by just training on shortest paths. So this is the result based on vertex query model. Next, we have also some results for comparison of many constant length chain of thoughts with a long polynomial length chain of thought. So previous works had shown like the advantage of chain of thought by comparing to no chain of thought regime. But here we compare a polynomial length chain of thought with many constant length chain of thought. And the result is that a single chain of thought of polynomial length can solve this task, while for any constant number of chain of thoughts of constant length, then there is no hope to learn the task. And the proof ingredient for the positivity case, it's just following the previous results that chain of thought of length Tn can implement Turing machines in Tn. So because our task is solvable by like depth first search, which has a polynomial length trace, it can also solve it with polynomial length chain of thought. The parallel scaling case is just an extension of previous works on the expressivity of no chain of thought models. So we know that a TC0 circuit is a Boolean circuit with and or not and majority gates of potentially unbounded fan-in, and we can define a circuit family which is indexed by the size of the input of these TC0 circuits. And previous works have shown that any bounded depth softmax attention transformer uh, can be approximated by a TC0 function. So the class of functions it can solve is limited by the class of functions those TC0 functions can solve. And here what we show is that even aggregating constant length chain of thoughts is in TC0, and we just start by defining the autoregressive distribution for a transformer, and then we show that there is a TC0 function that approximates that uh, autoregressive distribution of the transformer. And next, we show that there is a TC0 function that its own distribution, not its autoregressive distribution, its own distribution simulates the autoregressive distribution of transformer. And because majority is one of the gates like in the TC0 class, you can take majority of those TC0 functions to have a TC0 solution for our task. And at the end, we provide a TC0 reduction from the L-complete classical ST connectivity problem to our own problem. So we show that uh, also taking majority over constant length chain of thoughts is limited to the TC0 class. And now I want to get back to the experiments and something I promised earlier. We observed that in the path model, we had some out of distribution successful traces where the model generated chains of thought longer than anything during training. So something we explored was just to apply an RL algorithm to reinforce those traces and see what happens. So what we basically did was that we just uh, generate many solutions from the model and then we verify them, and on those that get verified we just SFT the model on them. So just we fine tune the model on those verified chain of thoughts. This is just a very simple way of reinforcing those successful out of distribution traces. And what we observe as a result is that the model, through RL iterations, learns to exploit longer and longer chains of thought. So here the orange one shows the original model, which we discussed, but the other ones are after the RL iteration. So after one RL iteration, you see that the model learns to exploit longer chain of thoughts. And with further iterations, it learns to, at each sequential scale, it gets better and it also learns to exploit longer chain of thoughts. So you can see that the maximum length of chain of thought it generates increases as well as the accuracy for each sequential scale. So still the DFS model outperforms its performance, but by reinforcing those like backtracking traces, the intuition is that the model is trained to follow valid edges at training. So even when it gets to those out of distribution cases, sometimes it recovers from them by just following the edges back to the original path and continuing until it succeeds. So when you reinforce those traces, the model learns that backtracking behavior in some way, and its accuracy increases and its length of chain of thought. So although it was originally trained to output a path because of its limited expressivity and to perform finding a path, the RL does some natural sequential scaling. So the model learns to do something that is expressive enough to do it, which is closer to the DFS model. Just go to a path, and if it fails, just backtrack from it and then continue. So we can see the RL as a natural scaler of chain of thought here, and that's also observable for different depths. So here we plotted the accuracy for every depth we had trained on, and you see that the evidence accuracy is just the accuracy by verifying the chain of thoughts, as well as the decision accuracy increase. And besides them, the average length of chains of thought increases through RL iterations. And this is just reminiscent of what we saw like in the DeepSeek R1 paper, which the length of chain of thought was increasing besides the accuracy through oral iterations. And while some works have pointed out to uh, biases in oral algorithms such as GRPO, which would um, just favor longer uh, chains of thought, we observe that in our setting also, which doesn't use those methods, this behavior is replicated. And this could potentially provide one plausible explanation for this phenomena from the expressivity lens of view, that the RL is reinforcing uh, some algorithm which is more computable by the model. So, for example, if you have trained the model on just correct proofs or correct solutions, because the exploration and trial and error is inevitable, what RL does is that it reinforces those traces that were not in the training data, but they happen at inference because of the limited uh, look ahead of the model. So this is one plausible explanation, although it is very simplified, but could provide another lens of view. Uh, so I end here with our paper, but I also want to advertise some other work I've been working on, which is related to this case. The point is that we observed that the hope of chain of thought is to compute some to have a workspace for more computations. So you are given the question, then you can do computations and then reach a final answer. And if that's what's happening, and that's our hope, then making a chain of thought longer can enable more complicated computations and hopefully solving more complicated tasks, which is what we have seen like in these works on the expressivity of chain of models with chain of thought and a scaling chain of thought actually hopes that's the case. But in reality, something that's been observed is that sometimes the uh, direction is the other way. So the model pre-commits to some final answer in the beginning, and it just generates a chain of thought that justifies that pre-committed answer. And if that's the case, then just that's a barrier for sequential scaling. With just increasing the length of chain of thought, then you won't have more computation. And yeah, maybe it's also worth mentioning how people have seen this in practice. And one simple experiment, they do just counterfactual experiments. One simple one is that they gave a question to the model and asked it to generate a chain of thought and an answer, and then they inject a bias in the model that is pointing out to one of the uh, options as the solution, and they observe that the model very frequently switches its chain of thought to justify that biased answer and end with that answer without even mentioning that it's relying on that injected bias. So because this is a barrier to scaling, we study detecting this behavior in the internal representations of the model, because that behavior is not observable in the chain of thought. When the model is not faithful, it doesn't mention it in its chain of thought. So we look at the internal representations of the model and we are able to detect this behavior. And we are also exploring the ways to mitigate this behavior so that sequential scaling could potentially improve. And here I end my presentation, which was based on a joint work with Ezra, Enric, Aaron, Sami, and my advisor, Misha Belkin. Thank you so much. And would be happy to answer your questions.